Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. I guess this is the perfect slide to start on. Right now, we're going to be doing a research stream for the next few hours. Now, I know a lot of you guys know what the deal is with these streams. Basically, the idea is I want to present research in a way that is enjoyable for people to watch, and I don't really know how to do that. So this is an attempt at just kind of showing research to people, doing research with people in a very open and engaging way. If it works, that's great. If it doesn't work, well, we'll try to fix it and make it work. C252, Jerry Licious, thank you guys so much for coming in. If you guys have any questions, comments, concerns, feel free to let me know, and I'll totally address them as soon as I see them in chat. So let's do page before, and let's talk about what we're doing today, because it's been a few weeks since we did a research stream. As you guys know, the code base that we're working on right now is GPUE, which I can get you guys a link to in just a second. We go here. If I just look for GPUE, can I find it? Nice, this has to be it. Here it is, right here. So this is, I guess I can just paste it there. The code base I use for work. Admittedly, it's not incredibly popular. It's like 1/1000th as popular as the algorithm archive. But it's useful for a number of different reasons. In particular, it is the fastest superfluid simulator of its type. And that's impressive, and it's useful for various different purposes. Let's see, finally finished switching the springs back on my speed cubes. Oh yeah, good. I too spend late Tuesday nights talking about massively parallel multi-component superfluid simulations of bosons and condensates and graphical processing units, and even more big words. I'm gonna be honest, like, when it comes to research, oh, I'm sorry, I just hit the microphone. 1/100th, yeah, you're right. When I read papers and stuff like that, there's certain things that I like reading, you know, like when I go to the archive, right? Like, I guess this goes into the Veritasium discussion we had before. Let me just go to the archive right here. There are certain things that are clickbait to certain people, right? Like if you say, here are 5 ways that climate change is going to blow your mind, like that'll make some people click. You know, undoubtedly it'll make some people click, but the things that will make me click, like the things that will make me really want to read your paper or something, can all be found here. I don't know why, like when I read a paper, it's just like Montague semantics for Lambic pregroups. I know none of those words, and somehow I want to click because I'm like, I have no idea what that means. Or down here, FPGA, I like FPGA, super cool. So dynamic vision sensor integration on FPGA, cellular neural network, I assume, accelerators for high speed visual classifications. Like, I don't know, it just makes me excited when I see stuff I don't know. And that's kind of my type of clickbait. Ooh, speeding up the Karatsuba algorithm. Karatsuba must be. Anyway, it's super cool. This is the kind of stuff I like. Convolutional neural network. Oh yeah, you're right. It's convolutional. I'm sorry, I'm an idiot. I was reading up on cellular neural networks not so long ago, so I think I just kind of got it all confused in my head. Is it really worth researching if there's isn't at least 5 big words? Sir Komodo, that stream title makes me feel like I'm in Star Trek. Yeah, honestly, the idea here is I'm trying to clickbait people like me. I'm not trying to clickbait, you know, the general Twitch audience. I'm just trying to get people who might be interested in this type of stuff. And so I'm not going to write research stream. I'm going to write what we're actually doing with the hope of getting people interested and involved, you know? But we'll see how it goes. You know, this is really, there aren't so many people besides like Raimu, who came in earlier today, who, is it Raimu or is it? Anyway, who actually talk about like open research and stuff like that. Hey Fletcher, how are you? I think I already said hey to you. I don't know. FD God, how are you? Okay, we are everywhere. Real light, that's it. I'm sorry. I always get the two confused because they have such a similar name. Doko, how are you? Zdoko? Is it Tokdo? Zitokdo? I don't know. I honestly, I'm very bad at pronouncing it. I can see the first part of the title until condensate so. Yeah, so let's talk about what we're doing. So GPUE is the code base we're working on. This is a superfluid simulator. No, in actuality, it is a simulator of a Bose-Einstein condensate, which is a type of superfluid. But for the purposes of this particular stream, it doesn't really matter. It is a superfluid simulator. We are simulating superfluid systems. Now, how does this work? Well, okay, we have an atom, right? The atom has you know, a bunch of electrons and protons and neutrons in it. So here we have 2 electrons here, and here we have, what is it, 1, 2, 3, 4, 5, 6 electrons out there. I think it's 2, 6, 8. I don't remember what it is. Anyway, point is, each of these electrons have a spin associated with them, up, down, whatever. You know how it goes. They all have spins associated with them. If you add up all the spins and you get an integer value, you get something known as a boson. And if you add them all together and you get a half integer value, you get something known as a fermion. These guys act differently as you cool them down to absolute 0 Kelvin. So basically, you add up all the spins. Each element of your atom has a half integer spin. It's spin up, spin down, something like that. You add it all together. If you get 1 spin left over, you're a fermion. If you have no spins left over, you're a boson. As you cool these down to near absolute 0 Kelvin, weird things start to happen. Fermions go by Fermi-Dirac statistics, which basically mean they kind of pair up in orbitals. Bosons, on the other hand, as you cool them down to near absolute 0, all condense into the same macroscopic giant particle that happens to be a superfluid. So we are dealing with bosonic systems, in particular something known as a Bose-Einstein condensate, which is a thing that happens when you put bosons into near absolute 0 Kelvin and they condense into the single particle, right? It's called a Bose-Einstein condensate. And that's what we're working with here. So we're working with bosons, really, really cold bosons, like 10 to the 5, really, really cold bosons. FDGod92, thank you so much for following. Okay, so let me go ahead and move down here, and let's talk about what exactly we're doing with this simulation. Okay, so let's say we have a superfluid that looks something like this. So it's just a giant particle. It's been condensed into this giant blob, right? If we rotate this blob, let's say rotate it like this, we're going to get a whole bunch of vortices. These are little tornadoes that pierce our blob, our condensate, from top to bottom, right? Now I'm putting these in a very particular fashion. This is a triangular lattice because that's what they form when you rotate them really quickly. This is staunchly different than what happens in classical fluids. If you rotate a classical fluid, something like this, I've done this many times before, but you rotate it, you get a tornado. I don't know if you can see that, but you guys know what a tornado looks like, right? Some sort of circulation. In a quantum superfluid, right? The circulation, like was stated by Atom Fighter 10101, is quantized. This means that every single vortex has a quantized amount of vorticity around it. So if you rotate faster and faster, giving it more and more angular momentum, rather than creating like a larger vortex, multiple smaller vortices will form. Now, because there is no resistance in a superfluid, these vortices don't just kind of randomly end at any point. So like if you rotate a glass of water, let's say, you'll get a vortex that looks like this, right? But the vortex could end here. It could just stop. This doesn't happen in a superfluid. What happens in a superfluid, and let's pretend you have a cup of a superfluid, is you get a vortex that looks like this here, something like this, and notably it ends at the very, very base of the superfluid down there. So the idea here is that your vortex will keep going until it hits a wall or another vortex. And this is also interesting, right? So we have recently published a paper in 2-dimensional vortex dynamics. I'll go ahead and give you guys a link there. Let me just go ahead and Google myself, G here. It's an interesting paper. I would definitely suggest looking at it if you want. But we already discussed it in a bunch of detail. So I wasn't advertising this too much because it wasn't open access until recently, but now it's open access, so please feel free to take a look and see what you think. Okay, and so again, we did a paper on chaotic vortex dynamics in 2 dimensions, and I'm currently writing a paper for vortex structures and different vortex ring generations, things that we can make in 3D, and that's where we're at now. So kind of what we're working on. Let's see, what do we have here? I'm gonna go ahead and catch up on chat. Duralicious massively parallel multi-component super. Yes, that's what it is. Oh yeah. Circulation, conservation of angular momentum. You're saying the right stuff, Atom Fighter. Now, where do you buy a superfluid? So superfluids come in basically 3 different forms. You've got the neutron star. You have the superfluid helium-4. And then you have the Bose-Einstein condensate. There are other things that act like a superfluid, but these are the three main superfluids people talk about. Unfortunately, you can't buy a neutron star unless you're like a Time Lord or something like that. So you can't get that. You also really can't buy these guys. They're super hard to generate. BEC is what we're talking about here, but basically if you take a certain isotope of helium, you cool it down to, I think roughly 4 Kelvin, it goes through a second order phase transition to become a superfluid. So you can also use that. The problem is helium-4 and neutron stars are both kind of, I'm not going to call them lossy, but they're kind of not pure superfluids. That is to say, there is some regular fluid component, or in the case of a neutron star, a magnetohydrodynamic component. That means that you don't get the pure superfluid dynamics. With the Bose-Einstein condensate, you get basically exactly what you simulate. It's really cool. You need helium-4. Yeah, I'm honestly not sure how these experiments go. The helium-4 experiments. Just being water and tonic water. Yeah, okay. Keeping along with this conversation, let me just go ahead and create a new page before. Keeping along with this conversation, I suppose there's a bit more that we should talk about here. So you guys know the Schrodinger equation, right? IH bar d phi psi over dt equals, I'm just going to put p squared over 2m plus v naught as some sort of trapping potential. I'm going to leave some space, and then I'm just going to multiply this by psi at the end, okay? So this is the classical Schrodinger equation. Not classical, it's quantum. This is the Schrodinger equation, right? Schrodinger. I always mispronounce it. Let's see. What do we have here? Can we just buy it and turn it into an isotope? I have no idea. Why Schrodinger? Wait, let me explain what we're doing here. So this is the Schrodinger equation. This guy over here is basically showing the dependence of psi with time. That's what this d over dt is saying. And then we have two components over here, something in momentum space and something in real space, right? So these components, one is the, again, like just some sort of grid in momentum space that we are traversing through. The other guy over here is something known as a trapping potential. Now, we've done a lot of quantum stuff before, and again, I'm just going through this. It doesn't have Dirac on it. Wait, what are we talking about? So we're not doing Fermi-Dirac statistics. We're doing Bose-Einstein statistics here. There isn't really much to do with Dirac here at all. At least for these simulations, we don't deal with anything with Dirac on it. So, I mean, we literally get all the dynamics we need off of a variation of the Schrodinger equation. So that's why I'm going through it. Also, I know everyone pronounces it Schrodinger. For some reason, I just have it in my head to pronounce Schrodinger. Anyway, point is the trapping potential is like some sort of cup or something to hold our particles in. So if we have some sort of like x squared harmonic trapping potential, our superfluid will kind of rest somewhere in there like that. Now, for a Bose-Einstein condensate, right, we're not dealing with 1 or 2 or 3 particles. We're dealing with thousands of particles, right? And all of these particles interact with each other. So what we do is we add in an additional term here, which is a g psi squared, which deals with the interaction between all of the particles, right? And this allows us to basically simulate our superfluid Bose-Einstein condensate, right? By allowing us to deal with the interaction term and all this kind of stuff. Basically, by solving the Schrodinger equation with time, we can get any of the dynamics we need for our superfluid system. And that's kind of where we're at right now, simulating this system in here. Let me try this one more time. Oh, hello, Control Y. Yeah, simulating this system in here, right? So that's where we're at. The left-hand side is the work, and the right-hand side is the change in energy. Circulation deals with conservation of angular momentum. Yeah, you can see it that way. Okay, so yeah, this is what we have. We're basically solving this equation. This is known as the Gross-Pdevsky equation. Gross-Pdevsky. It's for the most part the equation that we're solving for this system. If you go to another paper I've recently published, let's just go back here to GPUE. This kind of talks a little bit about it, but not so much. We'll have another paper coming out soon that discusses the code in more detail. But that's kind of where we're at there. Okay, again, you don't have to read the paper. Just if you have questions, let me know, and I'll address them as soon as I can. Okay, so by solving the Gross-Pdevsky equation, we can basically get all the dynamics of the system that we want, which is really cool because that means that we get exactly what experimentalists see by just simulating a system. Now, here's where the GPUE code base comes in. It is the GPU-based Gross-Pdevsky equation solver. We focus specifically on vortex dynamics and things like that. So basically we take that Schrodinger equation we had before, the Gross-Pedievsky equation. Again, I'm just going to write it out again because I didn't have enough space before. D psi over dt is going to be equal to IH bar. I just did IH bar twice, didn't I? Should just be P squared over 2m. And actually, I'm going to leave a little bit of space here too to explain some more stuff. So I'm just going to put a parentheses around there, squared, plus V naught plus G psi squared psi, okay? So what we can do is we can add an angular momentum component to this, where we subtract out an omega LZ, where omega is some sort of rotational frequency, and LZ is an angular momentum operator, usually like xp sub y minus yp sub x, right? So this basically means we're adding in some sort of gradients in the x and y direction here, which allows for us to add a rotation to the system. Now, in general, we don't have to add a rotation. We can add something else known as a gauge field, right? So this rotation becomes actually a part of the Gross-Pedievsky equation by adding in a minus ma term in here. So this term here turns into two separate gauge fields, ax, which is going to be equal to y, and ay, which is going to be equal to x. And if you do the math, it kind of turns out to be the same thing. So by adding in all of our rotational fields as some sort of gauge field, we're actually able to do a whole bunch of very interesting like vortex structures and stuff like that that you couldn't generate with just rotation, because now we're not really just rotating the system. We're adding in a specific field that's varying based on the geometric like distribution of light or something like this. So we can basically imprint any structure we want onto our system. Now, for the most part, this goes into another paper that I'm going to be submitting soon. In fact, I'm going to be working on that this afternoon. But for now, I want to talk about what we need to do for the next steps of the GPUE code base. So let me go ahead and pause for a second because I'm moving super quickly, and it's kind of under the assumption that people have seen this before, but admittedly, because I haven't done this in a few weeks, I've got a feeling that there's a lot of people who are probably a little bit lost. So if you guys have questions on any of these topics in here, so superfluids, gauge fields, Schrodinger equation, I'm just gonna write Schrodi, any of these guys, let me know, and I will, I'll totally address those right now. So just let me know, and I'll attack those guys. Let me get some water real quick. And if you have no questions, I'll just keep going. Because again, I don't want to spend too much time on the background here, maybe another 15 minutes or so, before moving on to the next stuff. I've literally done all this stuff in the past. Yeah, I know, actually, a lot of people in this chat, like we've actually got some people who have PhDs in like theoretical chemistry or computational chemistry and stuff like that in the chat. It's quite impressive. This community here is genuinely impressive, and I'm a big fan. I'm a biomedical engineer. Oh, nice. What kind of stuff do you do? 1 second. Oh, I just got some weird notes. Oh. Okay, cool. So again, this is my work time right now, so I need to be kind of careful that I'm not, you know, missing a meeting or anything like that. Let's see. Right now I'm unemployed. Oh yeah, okay, cool. No problem. We have a lot of chemists in the Algorithm Archive community. I think we have a few chemists, not a lot, a few. Okay, so since we don't have any questions, I'm going to assume that everyone that is lost, or everyone that I have lost up to this point, has left. So now we're left with the core crew of people who know what we're talking about. Okay, so we've talked a bit about the Gross-Pedievsky equation. Now let's talk a bit about GPUs. I've done quite a few GPU streams, at least recently, and these GPU streams are all, I mean, it's all about what GPU computing is, why it's important, all this kind of stuff. Suffice it to say that the GPU is a card that you slot into your computer that has a whole bunch of different computational cores. This allows you to basically take your problem, split it up into a whole bunch of little itty-bitty problems, and send each one of these problems to a separate GPU core. This means that by sending them all out and parallelizing the work such that you do everything at the same time, you can actually get massive speedups in your runtime of your code just by basically sending it to a different device to do the computation. And that's kind of the heart of GPU computing. So GPUE is basically taking the gross PDSC equation, solving it with an algorithm known as the split operator method, which again is in the algorithm archive, and then distributing that onto the GPU. And that's where we're at right now. Now, there's a few features that people are requesting. One is going to be multi-component simulations, multi-component. Another that people are requesting is dynamic fields. And the last one that people are requesting is I'm going to write down CSSFM, which stands for the compressed split-step Fourier method. Okay, so these are the three things that people are requesting, and let me explain each one in detail. I guess which one of these sounds most interesting? You guys talk to me, and then I'll talk about whichever one you guys want to talk about first. So a multi-component simulation is a simulation where we have more than one superfluid in the same simulation. So that means we have two superfluids all kind of working together, or 3 or 4 or 7 n superfluids all working together in the same simulation. This is difficult for various reasons, and if that sounds interesting, talk to me about that. Dynamic fields are essentially allowing us to have fields that are dependent on time. So a potential that's dependent on time, or other variables that are dependent on time. These are useful for applications. And finally, compressed split-step Fourier method is the act of taking the data that we have and compressing it so that we no longer use literally petabytes of data. Or, okay, fine, petabytes might be too much, but a large amount of data during every simulation. So it's usually terabytes of space. But why do we need multiple superfluids to be simulated at the same time? Yeah, okay, let's do multi-component first. Karth42, thank you so much for following, really appreciate it. Yeah, so we'll do multi-component first, and I will talk about the other ones, but we'll talk about what multi-component gives for us. First of all, why are multi-component simulations interesting? So let's imagine that we have a superfluid that's on a ring, okay? So everything in this white space, I'm going to put 2 different superfluids in here. One is going to be blue, and it's just going to go up here, and the other is going to be green, and it's just going to be on this side, right? So we have, on the one side, one component, which is blue, and on the other side, another component, which is green. Now, like I said before, if we rotate a superfluid, right, we get a whole bunch of quantum vortices. Right, because as you add angular momentum, we expect for rotation to act a particular way. What one of the researchers in our lab found is that if you rotate this system here, oh, that was a weird arrow. Let's try doing that one again. If we rotate this system here, at a certain velocity, not necessarily fast enough to generate a vortex, these boundaries here move in a very, very weird way. You would expect some sort of quantum motion. You would expect some sort of, I guess, rotation that acts like, well, quantum rotation, right? But what we see is that these boundaries actually move in a very classical way. They just kind of rotate around, which is super bizarre. It means that for some reason, when you put multiple components together, their interaction is somehow somewhat classical. And this is kind of a very weird and bizarre thing to think about. And also, there are different ways in which you can mess around with these components, right? So let's say instead of having a clear boundary between these 2 components, these components were immiscible, which means that you can't tell the difference between them. Well, in that case, now you've got this weird superfluid that's a mix between 2 different superfluids. It's really, really weird. And that's another case that's kind of interesting for multi-component simulations. There are other people that have proposed doing a simulation that looks something like this, where we have a trapping potential here, and we've got one component sitting in somewhere in the center, and then we have another component, which I'll do in red, kind of just oscillating back and forth, just kind of going in and out of this trap, right? And the question is, how exactly does a second component interfere with the first component, right? Could we use that to get work out of the system, you know? This type of stuff. There's a lot of questions as to how we can utilize or how we can use 2 different components to do a whole bunch of different interesting stuff. Bulk statistics tend to be classical. Yeah, I mean, that's what we're finding, right? It's just kind of an interesting thing that, to me, it was super interesting because the rotation genuinely, there were some funky things about the rotation. I can probably pull up a paper for you if you want. Let me see, where's Angela White? Let's see if she has it here. Cited by as non-classical velocities, probably if I just go by year, I can find it. Of course, she published a whole bunch of papers. More superlattice structures, kick emergent classical rotation. probably this guy, is what I'm looking for here. PDF. Can I get the PDF? No, it's okay. Well, anyway, here's the paper. We can probably find it on the archive real quick. Let's go there. Archive. So here's a paper from our unit that did this kind of stuff. I hope they're okay with me talking about this. I think they should be. I didn't ask them beforehand. But yeah, so we have, in particular, this kind of weird, I don't know how to put it, but this weird boundary between the miscible and immiscible regime, where you see things start to act like the bulk statistics, like we said before, and things start to act like the very quantum angular. So here we're basically increasing rotation, right? And in a quantum regime, you expect these steps to happen, where you expect angular momentum to be introduced in a quantized way, like you just get steps of angular momentum. But as the interaction increases, right? So we're getting increasing the interaction term. We start to see it acts more like just classical rotation, where it all rotates at the same speed. So this is an interesting paper that talks about that. Oh, there was no H there. What's there? Let's try that one more time. Wave function of interaction results. Phi times phi, magnitude of phi squared, magnitude of phi b squared. Yeah, that's correct. It's pretty correct, since there are last two terms here. Phi times phi x exp. Yeah, I mean, that looks correct. I mean, that's fair, right? The main thing is you have to deal with how they interact, right? And the interaction term is important. You need a general form of a bulk style. Yeah, I don't know. I don't know exactly what you're getting at there. Okay. So anyway, we have this type of rotation here too. Cool. Okay. So that's kind of what I was talking about there. So there's a whole bunch of other reasons why why it might be interesting to do multi-component simulations. In particular, the work we need to do to GPUE to get this done is unfortunately a lot. We have a lot of work to do. So basically, the way GPUE was set up is to work with only a single component, right? So this means we have a single phi, or psi. But now we need basically an array of psis, right? And so this means that we have to kind of go through all of the previous code and make it so that we're allocating a full array instead of just allocating a single component. And this is kind of a pain, but most of it's done. It's a logic that is why they don't teach quantum physics to engineers. You get general form of bulk style when objects interact. It's the logic that is why they don't teach quantum physics to engineers. They do teach quantum physics to engineers, though. I mean, there's a lot of engineers who are dealing with quantum physics right now in, like, for example, Intel and stuff like that. Basically, they're getting to a point where they can't get any smaller with the processors and stuff like that. So basically, turning this into an array is the primary challenge of GPUE for multi-component simulation. The next one I'll talk about is dynamic fields. Okay, so let's just talk about that. This is basically the act of having a potential that changes with time. Now, we already have this in the system, right? And at first, this doesn't seem like something that would be particularly challenging to create, right? But let me explain why this is a pain. First of all, we would like the users to be able to implement their own potential, right? So if they want their v of t to be equal to x squared plus 7t, I don't know why they'd want this, but let's pretend that's what they actually want. Then we, in principle, should allow the user to implement whatever field they want. This means that, well, they're going to have to write down their equation in some way, which is actually kind of a bit of a problem, right? Because GPUE is already compiled, right? So if you're going to write down your equation, then we're going to run into a situation where we're going to have to compile this during runtime, which is kind of sort of what we've done. We've implemented something known as an abstract syntax tree, which will represent this guy as maybe a plus operator of a multiplication operator of 7 and t, and another multiplication operator of x and x. And in this way, we save it as basically a tree of operations that need to be done at any given moment in time, instead of saving it as some sort of bulk array or something like this. This has the advantage that we don't need to store as much data on the GPU, but it also has the disadvantage that now we're going to have to basically regenerate this v every time step, right? Again, the big advantage is that we save memory, but the disadvantage is it usually comes with the cost of performance. Now, in particular, people don't care so much about VFT. I mean, they do care a lot about VFT, right? Like, because you can do a whole bunch of really cool, like, shortcuts to adiabaticity and do some really cool stuff with a dynamic V. But they also care about other variables. What if you want the interaction to change with time? Or what if you want whatever variable you want to change with time, right? Usually interactions are the one they care about. But what about omega, the rotation speed? Could be a function of time. There's a lot of other things that could be a function of time. And right now in GPUE, we don't really have the ability to have other things as factors of time. So this is another part that we have to work on. This is another thing that we're looking at. And finally, I want to talk about the CSFM method. So this is the act of basically, again, taking the data that's in GPUE, compressing it to the point that it is incredibly small, and then running a simulation on the compressed wave function. This has the advantage, again, of saving data, right? And I don't know if I've harped on this enough, but one big problem we're having with GPUE right now is that it just has an insane storage footprint. That is to say that basically every time you run the code, you get way too much data out. And it just takes way too much time doing like basic matrix multiplications because the amount of data that it has to store is very large. And now I know what you're saying. It's not actually too large, right? Because it can fit on a GPU, but it's still large enough that, you know, we've used basically 100 terabytes of data, or well, at least 50 terabytes of data on our local supercomputer. And because of that, we need to find a way to basically store less data on our supercomputer, especially because our new supercomputer will will allow the users to have much less space in our current supercomputer. They're switching to an SSD system, which means that it will be, you know, obviously solid state, which is faster, but also has less storage capabilities. So we need to kind of fix this before I leave. This is actually the project that Ben, or that one of the interns will be working on. We hired an intern. They'll be working on this project, and it should be pretty interesting. But this project I'm not going to work on here on stream just yet. We'll talk about compressed sensing in a bit, and we'll do all this kind of stuff, but that's not the purpose of today's stream. Today's stream will be either working on the multi-component simulations or working on the dynamic field simulation. Partial projection is advantageous because it feels more like natural systems. I don't know what we're talking about here for partial projections, actually. Let me go and get some water real quick, and then we'll go ahead and hop on to this. And again, guys, this is kind of an attempt to just do research in a very public way. So if there are things that are working or things that are not working, if you think it's not really worth doing this kind of arcane stuff on stream, I do totally understand. So just let me know what you guys are thinking. I personally would like to do more research streams. I just haven't quite figured out how to do them. You know, I feel like I'm missing something to make them like super exciting and engaging for people. So if you have questions, let me know. The amount of stuff that Ben knows is really neat. Yep, I'm quite impressed. I'm hoping this internship project goes very well. Because the coolest thing about this internship project that's coming up is like, it was advertised on YouTube. We did most of the research here on Twitch. Like, it's just completely open. You know, the paper is going to be open at the end. Everything about it is open, and that's really cool. The hard part for me is that I have to put my full attention to all the details. For like research streams and stuff like that, yeah, I understand that that's a problem, and it's not really something I can fix. Most streams I tend to put on while working. Yeah, that's true. I've thought about doing something kind of like what they do with art streams, where I don't really talk about like what I'm actually doing, and I just have you guys on in the background and just kind of chat. But I don't know, I feel like I don't really like that so much. I feel like we should talk about the science and research and stuff behind it. I don't know, it's stuff to think about. Okay, so let's see, which one do you guys think is more interesting then? Please don't do that. I don't know. I mean, it's something I've thought about. I think it's fine the way you do it. Okay, cool. At least we have 2 people out of the 11 people watching. Okay. So if you guys have questions, comments, concerns at this point in time, let me know, because I'm going to move on to the next bit, which is where we actually start doing implementations and stuff. So it's 9:30 in the morning. I'm going to try to keep this up until noon, but we'll see what happens. You know, usually when I try to do these streams, like something absolutely bizarre happens and I'm like, I have no idea what's going on. And then I have to go into work and think about it a bit and just kind of ruminate and, you know, 9 people, that's an even better ratio. Yeah, I don't know. I was just looking at the statistics over here. Okay, so I'm gonna go ahead and CD into projects GPUE over here, and same thing over here. CD projects GPUE +1. Let's see. I wish I could transport the 5% of information in my brain to your brain that maybe you don't know. Oh, there's probably a lot of information I don't know, if I'm being honest. I'm not here and I'm not trying to pretend like I know more than other people. I know more about specific, niche areas that I study, sure. But that doesn't mean I know more in general than other people. And I think that's one thing a lot of people have trouble understanding about academics, I feel. Like, I think a lot of people tend to feel that academics are incredibly arrogant and they talk down to people and all that kind of stuff. But in my experience, that's not the case. In my experience, most academics do a pretty good job of, how do I put this? Do a pretty good job of, understanding their scope and not going beyond that scope. And I think maybe that's what offsets people. That's why people don't like it. I know you know more than me in a lot too. Yeah, but that's the thing. I don't think that I know more than everyone else in general. Like, I think that, sure, I know a bit more about specific things, but that's just because I've studied these specific things in detail for the past 5 years, Let me check which branch I'm on. Git branch. I should be on the development branch, so let's get poll origin development. And let me go ahead and also check on GitHub to make sure there isn't anything kind of weird. I'm gonna do git diff of source init. And it looks like there isn't that big of a difference. So it gets, well, let's just remove source init. Git poll origin development. That's how you do it. That is not how you use Git, just for the record. Okay, good. And I'm just gonna go ahead and make this. So cmake dot, and let's just make this real quick. Do a quick check simulation just to make sure everything works. Make. And while it's making, I'm gonna go ahead and go over here to github.com, and I'm just gonna take a look at these issues. See if there's anything we need here. Okay. So one thing I want to point out is I basically created a list of all of the issues that we have. There's some that are kind of more important to talk about than others. And this is the one I'm kind of working on right now, multi-component condensate simulations. Let me see if I have anything in here. So if you guys don't have a preference between the multi-component and the dynamic variables, I think I'll keep working on the multi-component since I'm like 50% done with the multi-component simulations. And then after the multi-component is done, I then have to redo the abstract syntax tree implementation anyway. So it's gonna be a bit of a challenge. So let me go ahead and run the unit test GPUE-U just to make sure it works. Give it just a second to do its thing. And then if the unit tests pass, I'm fairly confident in saying that the code should be working just fine. Now again, guys, let me know what you guys are thinking. I'd like to do more of these types of streams where we're genuinely doing cutting edge research and stuff like that. But it's difficult to do. It's difficult for people to see and understand what we're doing. So I do my best to describe it in the cleanest way possible. I can also run a quick vortex simulation, but I think we're beyond that at this point. Like, we did some vortex simulations before when we were checking the energy, but now I think the energy calculation is correct. I don't think we have any problems with that. Admittedly, the energy calculation uses way too much memory, but fine, fair enough. That's something that we can kind of work on. We have a working implementation so long as we have enough GPU memory available, which sometimes, admittedly, we don't. So I need to rework that implementation. In fact, let me go ahead and create an issue right now. Ho, did you guys see that? Oh man, if there's any latency, let me know. I feel like there might be. I have not dropped any frames, so I'm okay. But man, oh man. So let me go ahead and create a new issue. Let me just say energy calculation uses too much GPU memory. And let's see, I haven't already created curl function, test numerical accuracy, in the process of rewriting what is it? I can't understand anything of what you're doing, but I like terminals. Well, good, I'm glad you're here. If you have questions, just let me know. I totally understand that this is a bit arcane and kind of hard to follow and all that kind of stuff. So I'm doing my best to describe it in like the cleanest and most open way possible, but I'm human. I can't describe everything perfectly, and there's going to be issues with this. So just ask questions as they come along. In the process of rewriting the energy calculation for, I guess we're going to say rotation and, we'll just say rewriting the energy calculation. We needed a bit more memory. I only understand this at a very dumbed down and high level. Oh, I see what you mean. Fair enough. I can't even understand the title, so I think it's dead for me. That was kind of the point, you know, like, again, I put down a title that would be kind of clickbait for me, even though I know it's not clickbait for anyone else, but it is clickbait for me. We need a bit more memory than previously thought. As such, if we are running a memory intensive task, the energy calculation will not work correctly. We need to find one second. We need to find and rewrite it to minimize the memory footprint. I'm just going to create this issue and I'll take a look at it later. I've slowly but surely been using GitHub as like a bit of a lab notebook for me. Like, it's not a lab notebook. I know it's not a lab notebook, and I know I should be using project boards for this, but man, I just have been just creating issues. That's all I've been doing. Let's see. I can't even understand the title. He gave a description for about 15 minutes at the start of the stream. Yeah, it was clickbait for me. I can read it. I read it, that's why. I use Arch, by the way, image. You're talking about this guy? I do use Arch. I'm a big fan of Arch. Arch is my favorite distribution. And again, I know a lot of people in the Arch community are probably a bit arrogant about Arch, and I wish they weren't, but they are. But it's just, I like it. It's a nice distribution that does everything I want without any hassle. It's nice. Did you try rearrange the words in the title? Maybe it's a secret message. Everyone likes it. Yeah, I think that's the problem. I think a lot of people misinterpret the enthusiasm of the community as arrogance. I think there's just a lot of enthusiasm towards Arch Linux. Okay, so let's see what we have here for our implementation. I do know that the current implementation that we have does kind of sort of work, right? So let's go ahead and go into for multi-component simulations. Now what I'm going to do is I'm going to git log. And I'm going to see, actually, let me just go ahead and check the energy calculations. So let's go into VI. Where did I put that guy? I guess it's going to be source and probably, where did I put that guy? The energy calculation is going to be in splitop.cu, and I should have calc down here. Let's see what we have here. Is this the energy calculation with scalar molt, vector sum, adding in GPE? Yeah, okay, this should be correct. So we should have a derive function in here. Yes, good. So this is the new energy calculation, so I don't have to merge that in. We're good to go there. I'm French, so it would be really hard for me to do that. Oh, we have a lot of viewers from Europe too. I mean, a lot of people from Germany. I'm surprised you're up in France. Isn't it like past midnight or something your time? The problem is that there are some really annoying Arch hipsters, and then people assume that all Arch users are like that. Yeah, I mean, it's the same with everything, right? Like vegans, right? Like, I know a lot of very fun, friendly vegan people, but it always has this, people always think that vegans are just a bunch of chumps because you've got a few people that take the moral high ground about it, and they get kind of, I don't know, you know? Like, I hate telling people that I'm vegetarian because every time I do, people are like, oh, you're one of those people. I'm like, no, I'm not one of those people. It's just, I don't eat meat. It's fine. Haven't used Arch, always just used Ubuntu. That's fine. I mean, use what you want to use. I'm not going to force you to change your operating system just because I think, just because I like Arch doesn't mean that you have to use Arch, you know? The problem is that there are some really annoying Arch hipsters. As a neighbor of yours, I'm kind of in the same boat as you. Okay, so are you guys both from, Europe? Isn't it super late? I call myself a pseudo-vegan. I'll eat meat when with people, but at home, I only buy vegan foods. Yeah, that's fair too. I just find, I don't know, I cook almost all my own food, and it's just, I mean no offense to people who eat meat. Obviously, no offense meant. It's just that I tend to find the vegetarian food tastes just as good, is less expensive, and is, forces me to think a bit more about my diet, right? And that's kind of most of the reason why I do it. It kind of forces me to think a second about, hey, do I have the right amount of protein? Am I getting the right amount of iron? Is this dish, appropriate to eat? All this kind of stuff. It gives me a second to think about what I'm eating and putting into my mouth. And that's maybe most of the reason why I do it. And for environmental reasons, obviously. Okay, so let's go ahead and clear here. I'm gonna get off my soapbox there. I'm not gonna talk anymore about my diet because that's honestly not very important here. Instead, I'm just gonna run the SL command. Great, okay. Oh, it's readily available and cheap where you live? Yeah, that could be. Maybe it's just because I'm in Okinawa. Okay, so what I'm gonna do now is I'm going to just take a look at what we have for our multi-component simulation. So I'm gonna do a quick ls as source. So these are all the files we have in our source directory. We have data structures, stuff for dynamic fields, edge, evolution, example. I'm gonna run a very quick example of a simulation, just something super quick, and I'm going to see what it outputs. Because at this point it should output a different file than what a traditional simulation would output, right? So a non-multi-component simulation would output something slightly different. So I'm just gonna run GPUE/H, and I'm just gonna run this simulation here as an example, but I'm gonna modify it so it only runs on, we'll just do 256 by 256. That should be fast enough, I think, although I'm not honestly sure. So we'll give that guy a go. And while it's up, let me just go ahead and run NVIDIA SMI, and let's just watch that. Just to check our GPU memory. GPU is only using 101 megabytes, so we should be fine. I'm not too worried about that. Is the output graphical? It outputs files that we then plot. The problem is, I think the plotting scripts are not meant for multi-component stuff. So I'll show you guys the plot after this is done. Just give it a second to finish. In fact, let's just go ahead and go into the plotting scripts over here. So Control C, and let's go into VI pi, and we should have plot.py. Now we take a look at the data. Okay, so it actually looks like we didn't, it looks like it's still wave function 0 const. So it should be okay there. So if I go into cd pi, and I just run python plot.py input wave function grid size 256256 range 0 to, what is it, 50,000 and steps of 5,000. Yeah, this should do it. Okay, so here's our initial wave function that we have. It's just, blob sitting in space. It's 2D. What we're doing is we're running this simulation in imaginary time, which basically means that we are running it in such a way that rather than seeing the dynamics of the system, as you would expect in an experiment, we're actually just seeing the dynamics in this weird imaginary time space where we are losing all higher energy states. So every time step we move forward, we exponentially lose higher energy states. So we're just dropping in energy. We're just getting rid of the energy. And the hope is that we go to the lowest energy state. And in the lowest energy state, we should see a whole bunch of vortices in the system. So we should see them appear here. So what we're doing is we started with some sort of guess, and then we just rotated the system and tried to find the lowest energy state with rotation. So here we have all these little vortices that are appearing in the system. These are little tornadoes that are piercing our condensate from the top to bottom. Nice. And so this is about as far as we can go. But as you can see, we have a whole bunch of like weird quantum vortices in our system that we, if we move this further, we'd get them to form like a triangular lattice and stuff like that. But I don't care about moving it further. This is just a test to check to make sure everything's working as anticipated. Okay. I'm going to go ahead and remove all the data in our data directory here because it's just a chump directory, like just to store everything. And I just don't have a need to have the data up anymore. Okay, so now what I'm going to do is I'm going to run that same code we just ran, but this time I'm going to run some real-time steps in addition to the imaginary time steps. Okay. And the hope here is that we get a weird file out that is a bit different than the files I would normally see. Output from GPUE, because I did change the file output. And if we get these weird files, I'm going to plot those weird files, mess around with the plot.py script and stuff like that, so that we can basically start working on this multi-component stuff. So when it comes to the multi-component simulations, I'm going to be honest, it's basically just a bunch of, it's not engineering work. It's just a bunch of just grunt coding. That's all I have to do. Okay, cool. So now we're getting the real-time simulation done. So we just again, generated the imaginary time results. So we got, we lost some energy, and now we're working on the real time results. And I'm going to go ahead and check the data directory now. ls data. I'm back here. ls data. Okay. And it looks like nothing changed. It's still wave function e and wave function evi. So let's cd into pi, and let's just give this guy another go. So we're going to plot what we just plotted, except this time we're going to plot the real time steps. So here's the state that we started with last time, and we should just see it just die. Okay, or not. Okay, we're seeing the vortices kind of move around, but they're kind of moving around in a very weird way because we're rotating really, really fast, and we don't have enough vortices to support that fast rotation. So no matter what we have, we see these kind of like weird effects down here on the edge. Let me go ahead and zoom in there. See these kind of weird edge effects over here, just because more vortices are trying to form, but they can't form because, we're at some high energy state. It's just messy. It's just really messy. I mean, I can show you some other cool stuff there, but I don't think it's worth going into that any further. If you have questions, let me know, and I'll address those as I see them. Okay, so I'm going to go ahead and go into vi plot.py, and actually, I'm going to look at the output here. So let me go into vi source, and I think what I'm going to look for is... What am I looking for here? I guess evolution. And let me see where we have the right step. So if write it, so we're going to write it. We output double, we output... Okay, so file write out double. That's a write it step. If write it. Basically, I'm looking for the flag that allows us to write out data, right? So we have write out, and it's wave function array w, I plus step offset, file name. That's what I'm looking for here. Data directory plus file name. Okay, see what we have for file name. Okay, file name is wave function ev ramp and wave function ev. Okay, good. So I need to modify this file name then, such that it outputs a file that is respecting of the fact that we could have multiple components, right? So if you look at the data directory that we have now, let's go and look at that data directory, ls. What was that? ls data. Oh my gosh, come on. ls data. There we go. You notice that for the imaginary time simulation, we have wave function 0 const 1000, but for the real time, we have wave function ev 40,000, right? So this basically means that here we have wave function 0, signifying the first wave function, but here the output doesn't really signify that we could have multiple components in the system. So we're going to do wave function, and then I'm just going to do the same thing we have there. So it's wave function, and then this isn't going to be 0. It should be... how do you do this in C++? I guess it's going to be wave function here plus C string. Dagnabbit. Converting int to string C++. I'm sorry. I know there's like a bunch of different ways to do it. Usually string stream is what I see, but okay, can I just use toString? Let's try that. And then what am I actually looking for here? It should be wave function array W, so it should just be W. And then we should add a plus, and then we're going to do that. Okay, let's see if that makes. Okay, and then after it makes, we'll just run this one more time. And hopefully we get the right output now. And actually, while I'm here, let me see, what do we have for... I think I'm going to have to look for case 1 all the way up here. Oh my word. Oh my word. Where's our file name? And there. File name is wave function 0 ramp, wave function 0 const. These are no longer going to be wave function 0. It's now going to be wave function... what is it? It's going to be plus std toString. And it should just be W plus const. Something like this. And then we'll pop this down here too. Okay. Now we should have the file name basically done. Let's go ahead and make that guy. And then we'll run the same code that we just ran. Again, I know the chat's a bit quiet, so if you guys have questions, comments, concerns, anything like that, just let me know, and I'll address it as soon as I see it in chat. Okay, so after this is done, we should see the wave function 0 const file be the same as it was before. But now we should see a wave function 0 EV file, which is for the evolution. And again, this just allows us to have an evolution of multiple components of a wave function, right? Admittedly, we should probably really update the output files and stuff like this, because a lot of the, you have to just kind of know that the file is going to be in this directory, right? Like, we should probably allow people to modify the output file in any way that they want. But for now, I think we're okay. Unfortunately, just because we don't have a huge number of developers on this code base, it's basically just me right now. There's only so much we can do, It is currently the fastest superfluid simulator that we know of, so that's good. It's just kind of wish it was, we had a few more developers on it, but there's certainly not enough demand for more developers, so I'm okay with that. We have a GPUE group.github.io, GPUE group.github.io, a documentation page for this. So we'll be updating this too, but maybe not on stream, probably off the stream. I see C252, thanks so much for coming in. Have a wonderful afternoon, evening, whatever time have your time. See you next time. Okay, so we have that working now. Let's go ahead and take a look at what we have in the data directory. And it looks like we have, wave function 0 EV. So I'm going to go ahead and cd into pi, and then we're just going to go into plot.py, and let's see what we have here. Admittedly, this entire plotting file really just needs to be redone. It is not particularly good, but it is what it is. So let's see, class params, item, wave function. So I guess what I also need here is maybe another item for component. So let's just say component. I guess specifying component to use for plotting. And we're just gonna go here and just say comp is gonna be equal to 0 to start. Okay. Let's see, plot range. So we should be able to read in a different component then. So plot variable range. Where do we actually have the parser? Oh man, this is one of those things, isn't it? Print strings list. G is for grid. R is for range. And I guess I'm just going to do the same thing here. So we're just going to do yank. Now what am I looking at here? This is like the most just backwards parser I think I've ever seen for, I mean, admittedly I wrote it, right? So I guess I can say that, but man, it needs some work. So let's see, def parse args, I equals 0, parse equal to params, print string list. Well, I is less than the length of the string list, okay? We have data directory, I for item, R for range, and G for grid. I see what I'm doing then. Okay, so let's go ahead and do quick some DDs here, and let's just grab these guys up here. So we're gonna do yank for yank, paste it down here, and we're gonna do -C for component. And yeah, let's go. So the thing to component of the wave function variable. Thing to plot, that should be fine. So this is going to be C for component, par.item strings list I, but I'm not looking for item, I'm looking for component. Okay, so now we have the ability to basically read in different components, but it should be okay because the component is naturally set to be 0. Now, I guess what I'm going to do, def plot par item is wave function or wave function EV. Then let's see. I guess I'm just going to modify all of these guys so that they can read in a component. And then this should be okay. Yeah, I guess that's what I'll do. Let me go ahead and write this. And then after this is read in, we can basically do the same plot that we did before. Again, this is just a lot of grunt coding. So if you guys have questions or anything like that, just feel free to ask and I'll do what I can to answer them. 1 second. I need to check. I just got a message on my side screen. I have to check. let's see. Oh, okay, that was actually from me. That's fine. Okay. And I also need to check something over here real quick, and then I'll get back to it. Let's see. Again, I'd like to keep going until about maybe noon-ish my time. So we'll just keep going. And again, I'm not expecting this stream to be super popular either. So we'll just see how this goes. Not too worried about viewership here. It should be there. Okay, so now I just have to modify all of these guys, which should just be up here, such that they have a component value written. And I believe, let's see, what do we have here? Wave function cut, complex. Let's see, I think all of them need to be updated to have a component associated with them. So I guess I'm just gonna go to all the plot functions and just add in a comp. And then down here, when I'm doing the file, let's see, plot val. So plot wave function cut. We're gonna look for, how do we do this? It should be, I suppose, this will have a S there. Well, that didn't work. And this should also have a S there. And I guess it's gonna be, comp I? Is this how you do it in Python? I'm gonna have to take a look at that. Let's just do, what is it? String, what is it called? Dynamic strings? I don't remember what it's called. Format strings dynamically. SS Python, very good. Okay, so I need the parentheses around it. This is what I get for just not looking into this. So comp there, and then we should just be able to put a parentheses there and another one. We'll just put one down there. Here, and then we'll put another one here. So comp there, and then we'll just do the same thing. EV should be wave function underscore S there. S there. Cool. Okay. And I'm just gonna have to do this for all the plotting files. So let's just, or all the plotting functions. So I'll just kind of go down and do that. Plot wave function phase, comp, and we just do the same thing here. Comp I, and I'm just gonna check all these functions after they're done. I, and down here we're gonna do comp and I, and down here it's gonna be comp and I. Oh man, super engaging content. It's okay, it is what it is. Here and there. Oh. And then I guess we have to do the same thing here. So it's wave function S there and there. Okay, and we'll just keep going. Again, we have a few more functions to update. So now we have the component here. And then we just do it here. And then I guess there, and there. Why not do some lines? Why do some lines end in semicolons, some do not? Are there lines that, oh, because I don't know. I should probably fix that. That's me just forgetting Python syntax. I've been flipping between languages so much nowadays that I have trouble just remembering basic syntax for like literally any language. As long as it compiles, I'm fine with that. I should probably look for all the semicolons and get rid of them after this is done. Oops, that's my bad. Plot complex, so this is gonna be comp. Okay, now here's where things get a little bit fishy. Data directory, data real. So we're gonna start an increment. For the plot complex, I guess what I'm looking for here, we have the plot value, but then what we're gonna have to do is this S, and we're gonna have to do, and I guess it's gonna be component, but then we need to read in, I see. Okay, fair enough. So we have to modify this a bit so that we have an I value to read in, similar to what we had before. So it's gonna be S, and then we're gonna have to do chotomate comp, and then I should be correct. So again, I modified all of these so that they output, instead of just one value, they could output multiple different values for multiple different time steps. So I'm gonna have to modify these a bit. So we're gonna go in here and we're just gonna say for I in range, and then it's just gonna be start and increment. I guess I don't need this parentheses there, do I? And then I think I just do this for all of these guys. Something like that should work. Okay, so we'll keep going. And I'm just gonna hope this all works. We'll check it in just a second. I think it should all work. So here we're gonna have comp, and then I'll get rid of the semicolons. Because clearly I need to get rid of the semicolons. So we're gonna do comp I, down here, same thing there, there, and there. Okay, and we're gonna change this to the percentage S. There, there. Then we have to go down here. S. Don't delete any colons by accident though. Yeah, I mean, I'm gonna search for semicolons, right? Like, I shouldn't delete any colons if I'm searching for semicolons, you'd think. Let me get some water real quick. Oh my gosh, 1 second. There's a whole bunch of water that just fell out. I'll be right back. I have apparently a huge drinking problem. Okay, I'm back, sorry. Let's see, what do we have here? Looks like basically nothing changed, so we're okay. 1 second, now I have to throw this away. Yeah, so chat is super quiet today. I don't know if that's a good thing or a bad thing, but that's okay. I don't mind it too much. It's just, I've got a feeling, let's see, plot var range, so we're gonna do comp there. Oh, I see. The plot variable before. Well, let's just see if we can plot basic variables or not. We'll see what happens. I'm gonna try some stuff and we'll see what we can do. I'm trying to see if I can find this code. The code is available here. GPUE. So the algorithm archive is a bit different. So the algorithm archive is here, and we have a section on the split operator method down here. Here it is. So feel free to take a look at that too if you're interested. Yeah, admittedly, again, needs a bit of work, but this is one of the more complete chapters in the algorithm archive. I'm a fan. I also have a video on it. Because of course I have a video on it. Okay, so we'll just keep going. Plot value, this is plot variable range, but it should be, 1 second, the plot val. I'm gonna argue. I'm gonna argue that it should be the following. There, and it should be comp I, something like that. Data is data directory plus output. Yeah, okay. Should be fine. So we'll keep going. Plot variable here, and it's going to be So I guess plot variable is meant to plot a single variable and not a range of variables, right? So we're gonna have the component in here, and let's see, what do we have here? There should be data v is k not. What is this nonsense? What is this? Am I even using this function? Plus plot val. I'm gonna argue that this one probably doesn't need to be updated. Okay, let's pop down here. Where's our plot variable here? Again, I'm gonna argue it probably doesn't need to be updated. All right, right quit. So now I'm just gonna run some basic plots. So we're gonna plot, that wasn't right. We're gonna try this out. So Python, plot, I is gonna be the wave function, G is gonna be 256, range is gonna be 0 to 50,000 in steps of 5,000. And then the C, which is the component, should be 0. All right, here is our basic plot. Seems to work just fine, exactly as anticipated. So now we're going to try the same for our real-time evolution, the wave function underscore EV. Again, this whole plotting script needs to be redone. Okay, seems to be fine, nice. So now we're going to try plotting different variables, see what happens. Hopefully it works okay. So now we're going to plot just V. But we're not going to plot a range of U because we shouldn't have a range of V. And we're just going to plot this. Dang. Data V not found. Oh, I guess I'm going to have to do V underscore 0 underscore. That? Well, that's our potential. I guess it's only if we have a range. Okay, so here's the problem. I think our plotting script is correct for the wave function stuff, but I think I need to revert back some previous changes for the variable stuff. So let's go to vi plot.py, pop down here, and actually anything that we're plotting a variable and not a wave function, I think I'm going to remove the component stuff that we had before. So I think I'm just going to DT here. So that's for plot complex, and then we're going to do the same thing for plot variable range. Yeah, same thing here. Is there anything else that we need to update? No, so let's look for plot variable range and then plot complex. And again, we're just gonna have plot value I. Okay. And then the last one's plot complex, which is there and there. So again, we don't need the component in here. And down here, we're just going to do... Oh, interesting. You are correct. No, we're going to need it for plot complex. Yeah, okay. We'll keep it in there for plot complex. Yeah, we'll keep it in there for plot complex. But I think for plot variable range, why not? We'll keep it in there too. We'll just keep it in there for both of those guys. I was just being a bit pedantic, but it's okay. So let's go back to plot variable. There, and we're just, the component's already in there. Let's just go. It's easy enough. Okay. Something like that should be fine. So we don't have any variables with a range associated with them. So what I'm going to do is I'm just going to do plot, but I'm going to do v, and we're just going to do r 0, 0, 0 and see what happens. Let's do 0, 10 steps of 0. Argument 3 must not be 0, 10. Okay, plot 0, 10 not found. That is correct. It shouldn't be found. We should be plotting... Okay, at least we're looking in the right place, right? So let's go from 0 to 1 in steps of 10. It's not plotting the first one. Why is it not plotting the first one? So we should at least be plotting the... Where is it? we should at least be plotting v not not. We should be plotting this guy. But for some reason, it's not plotting it. Interesting. So let's go into via plot.py. Plot variable range. For I in range start and increment. Print I. Plot value. Oh, that's because I'm saving an image for that one for some reason. ls, what do we have here? ls star.png. V not not, is that it? Plot variable range. Here it is down there. What am I saving it as? I'm saving it as, oh, so it would have been Mirage. V12345 there. Yeah, okay, so that's the correct image. I'm okay with these modifications to the plot script for now. I don't want to go too much more into it. I kind of feel like I'm gonna have to redo all of the plotting at some point anyway, and I'm kind of feeling like I want to redo everything in Julia at this point because I don't know, maybe not the plotting. I'm not sure what I'm gonna do with the plotting script, if I'm being honest. The plotting script is the plotting script. It's just kind of a mess. But it's ultimately okay. You know, it's not so bad. We'll keep working on it, I guess. Okay, sorry, I was checking. Again, I got another notification, so I had to check the side screen. Okay, so that means we have the data output correct. That's one small step, but we have a whole bunch of other small steps to do. There's just a lot of stuff to do before this works for multi-component simulations. Now, what I've already done is I've already modified the wave function so that it reads in a wave function array at pretty much all places instead of just a wave function. You know what I'm saying? So like now it's basically an array of arrays that it reads in instead of just a single array. So in principle, we can just throw in a second component right now. There is no interaction between the components, but in principle, we could have multiple component simulations. In fact, I think I've even updated the GPUE help menu to reflect this. Let's see, what do we have here? Rotation, coordinates, card, component. Let me look for component. Let me just go here and just do file, VI file, and let's look for computing. No, I haven't updated it, so I need to update a lot of stuff. So we have to get the parser ready so that the parser has the multiple component capabilities in there. There's a lot of stuff to do. Okay. Yeah. Okay, so I guess we'll keep going. Yep, and we'll see how this goes. So let's see the backup directory. ls here. So we updated the plot file. That should be okay. Now let's see what else we need to update, or what else we can update now. Man, I'm starting to get a headache. It might just be because I've been streaming a lot today. Also, my voice is starting to go. So maybe we'll go till 11 today instead of 12. Usually I wanted to go till 12, but maybe we just go till 11. Again, this is kind of the first day doing one of these streams again, so I'm a bit rusty and we're not moving super fast, but that's okay. I wasn't honestly expecting to move that incredibly fast. What are all these bvox files? Let me do a quick du-h of the data, actually the Python directory. 482 megabytes. How much do I actually have? df df-h. Using most. I only have 13 gigabytes available. Maybe let me just run a du-h of this directory here. It's only 1.3 gigabytes. That's not as bad as I thought. It's still pretty bad, but it's not so bad. Okay, so let's go ahead, clear this guy. I'll run the SL command for good measure, and let me check this guy up here. GPU group issues. Let me see if I wrote anything else for the overhaul of plot.py. I didn't. I just wrote that it needs to be done. The plot.py is horribly undocumented and unclear. It needs a general rework. In addition, we need to make something similar for 3D, ideally, somehow incorporating gendata.py into the script. Bah. There's a lot of work there to be done too. Okay. ls again. ls source. So now we should have the ability to basically have multi-component simulations. Like, so we have the ability to output the file. We have our wave function array in our system so that we have the ability to run with multiple wave functions, right? Now we just need a way to specify our wave function number. So let me go into VI source and evolution, and I'm going to update the parser now so we have that ability, because I don't think we do now. I guess it's going to be, oh, we have so many flags. I don't even know what flags we have available. If flip, apply gauge, no, this is not what I'm looking for. Apply gauge is something else. Apply gauge, here it is. So we should have a giant loop over W, which is our wave function. W wave function array.size. Okay, so I suppose what we can do is we can just run GPUE with 2 wave functions, right? And then hopefully we'll just see what happens, you know? So let's go ahead and go through with that. So let me go into VI init, and let's see how we're initializing everything right now. Wave function array, and let's see, wave function array of wave function number. So where do we get wave function number from? Okay, vopt wave function number, wave function number. Okay, so we're storing wave function number. So I guess if we just go into VI source and parser.cu and go to wave function number, it should be here. Wave function number is 1. Ah, n. Of course it's n. Okay, so let's just try running the same simulation we ran before, just with an n of 2. So we're running with 2 wave functions. These will be non-interacting. They're not going to touch each other. They're just 2 separate wave functions, and I'm pretty sure something is going to break. I'm not sure what, but something is going to break. So let's go ahead and take a look at this here. So we're going to run the same code we just ran. Where are you, dog? There it is. Just with an n of 2. Run. Oh, it's doing something. No way this is working. Oh, if it's working, I'm excited. Nice. Okay. All right, we're going to let it go through the imaginary evolution and the real-time evolution, and we're just going to see what happens. Notably, it's taking much longer, which is probably correct. Let me do an NVIDIA SMI. Watch. NVIDIA SMI. Congrats so far. Yeah, okay. What do we have here? GPU is using 105 megabytes. Yeah, how are you, Art9K? I hope you're doing okay. This is very weird, because I believe just running it with a single component was using 105 megabytes. So this should use 210 megabytes, right? Well, let's just see what happens. It should output the appropriate files, I believe. So as long as it's outputting the appropriate files, we can plot it and see what happens. Wave function 0, and it is not outputting the appropriate files. Crap. Dag nabbit. Here I was thinking that it was working, but it's not outputting anything correctly. Let's just go and try running that one more time. Let's remove data star, and let's just run it one more time and just give it a second, just to make sure that all of this data that we had just generated was generated during the simulation. And then we'll try to figure out what the problem is. Try to figure out why the second component isn't running. So again, right now I'm just trying to run 2 components. Not interacting, just 2 separate components. They should look exactly the same. Joshua Goller, thank you so much for coming in. How are you today? I apologize if I misspelled that name, by the way, or mispronounced that name. All right, so I believe we are, yeah, it's not doing what we want it to do, which is okay. It's okay. We'll figure this out. What's this written in? This is written in C++ and CUDA. Predominantly CUDA. I mean, admittedly, I know CUDA is kind of like just an NVCC. Like, it's just essentially a C compiler, right? But a lot of it is just CUDA kernels and stuff like that. Okay, so again, we're not outputting the second component. I'm not sure if the second component is or is not. I'm not sure if it's there. So let me try running this again with an n equals 1, and let's see what happens. I feel like, oh, maybe it is the same seed. Maybe we're just not simulating this second n system. Okay, so we'll see what's being generated, what's not being generated. We'll see where we need to go from here. There's a lot of just small things that we're going to have to tweak. So I think I'm just going to run through the whole thing and just kind of see what is being done and what is working and what's not working, you know? I guess what I'm going to do is I'm also just going to plot this too, just to make sure that, you know, right now there's nothing wrong with what we're simulating, just to make sure it is working right now. And then after all this is done, I'm going to have to write a test for multi-component, but I have absolutely no idea. I have absolutely no idea what kind of test I need to write for multi-component. I suppose, like I said before, we've got these kind of miscible and immiscible cases, you know, something like this. And that would be a nice test. I have no idea how to do that. This would be a good test, like our immiscible regime, to see if the fluids mix or not. But I'm not sure how to do that. So I'm going to seed into Python, and I'm just going to run the last Python command. Oh, that wasn't what I was looking for. History grep plot. Oh, come on. And I'm going to want to grab, looks like 535 should be correct. Okay. Yeah, it looks like identical. What is a Bose-Einstein condensate? So I went through this before, but basically when you have an atom, all of the electrons and neutrons and protons all add up to some sort of spin in your atomic system, right? If all of these spins add together to an integer value, you have something known as a boson. If you cool bosons down to near absolute 0 Kelvin, the bosons all condense into one macroscopic boson, basically. And this is a superfluid, right? So our simulations here are superfluid simulations of Bose-Einstein condensates. And that's kind of what we're working on right now. It's just for some research, or it is for some research I'm doing, kind of for my thesis and stuff like that. I've got some papers and stuff you could read and all that kind of stuff if you're interested. Okay. So what I'm going to do, since that does seem to work, is I'm just going to go through and see why the initialization process doesn't seem to be working correctly. So let's go into VI source and parser. VI source and parser. And I'm going to look for wave function number. Okay, so here it is there, setting the default, and here it is there. Let me check to see, where were we before? So when we were running this, it should say argument for wave function number somewhere in here. Invalid option N. Oh, okay. So that would explain some of the problem. Wave function number. Okay. Wave function number. Okay, next. Case N. Okay, what I might have done is I might have forgotten to put it up here. Yeah, so maybe I need to put it here. And colon. Let's go ahead and make that. You should set up from... trust me, Raspberry Pis are not anywhere near powerful enough for this simulation. We're using, like, some of the best supercomputers around, and the reason we're running this code, right, or the reason I'm working on like, compressing the data and stuff for this code, is that we're actually using too much space on the supercomputers, you know? So, yeah, we're using supercomputers. So, in particular, I mean... we're using basically GPU nodes available on supercomputers. Also, I don't think you can put a GPU in a Raspberry Pi, can you? I don't think you could. Yeah, this is a highly specific computation that's only meant to be run on supercomputing systems. So, I mean, this is like cutting edge research type of thing. So it's not... I'm sure a built-in GPU on a Raspberry Pi is nowhere near powerful enough. Like we're using... P100s, actually V100s now. V100. It's the latest V100 NVIDIA. It's the latest NVIDIA Volta GPU. These are what we have in our data center or our supercomputer that we use. And again, it still takes literally a week to generate what we want to generate. You know, like using the best hardware available, it still takes a week. Using the best hardware and the fastest superfluid simulator in existence, which is one that we have, it still takes a week, you know? It used to take months. I mean, if you run this in like MATLAB or something, it's gonna take literally months to get the simulations we get out. It's quite a drastic difference. So now let me try running this one more time, and let's see where it breaks. Watch NVIDIA SMI. We are using 100 megabytes again. Did it recognize the option N? Argument for... Oh, no it did not because I didn't put it in there. Okay, What is it telling me? No option N again? Unknown option N. Why? VI source parser. G down here. Mate, I've always wondered how you interact with it. Do you SSH in and run it? Yeah, that's precisely what you do. So let's just give you a brief guide on how supercomputers work. I give this to a lot of people at work. So when you're doing when you're simulating stuff on a supercomputer, you have your own computer here. So here's you. What you do is you log into a login node. So this is a login node. And this is where like hundreds of users are on here. So we'll say 100 different people are all on the login node, right? So you SSH onto the login node. The login node then has access to all of these nodes over here. Let me try drawing that a bit cleaner. Can I just draw a box? Yeah, maybe something like that should do it. So all of these nodes over here, right? These are all just different computers to do your computation on, right? So the login node will allow you to have access to whatever nodes you want, right, to do your computation. So what you do is you submit your code at the login node. It runs on these computers over here. And then when it's done, you just kind of take the data. Do you only get a percentage available processing power? It's not, you don't really, in a sense, yeah. So what you do is you have particular limits that are available to you by, like, set by the scheduler, right? So basically, like, okay, here you are on the login node, right? You write some code. Then you submit it to these nodes over here, right? Chances are all of the nodes are in use, or a lot of the nodes are in use. You simply don't have the compute space to do your code, right? So you requested, let's say, 8 hours of runtime, and you requested maybe 4 CPUs to run your code on, right? Maybe 4 CPUs are not available, right? And certainly maybe 4 CPUs are not available for the next 8 hours. You know what I'm saying? So it could be that when you submit your code, it takes maybe an hour or two for the space to become available for you to run your code on, right? So you usually can only use a very, very small fraction of the available processing power because the scheduler will have to place your job somewhere in the queue. If you're using 50% of the available processing power, well, that means that it needs to free up 50% of the space available. And quite frankly, it's not going to do that, right? How do you get back your results? I mean, it outputs to a data file, very similar to how we're doing it here. So in this case, like for example, Control C, if I do an ls of the data directory, we get our data here, and then you just transfer it to your own machine and you plot it, similar to what we've been doing here. It's the same workflow. You have some sort of data, you do the simulation, you get some data out, and then you just plot it, manipulate it, do whatever you want from there. The big thing about supercomputers is that you're always fighting with the scheduler. Again, because a supercomputer is a very, very heavily used resource. You have to make sure that your code, you basically request the minimum amount of resources such that your code will run completely. You know what I'm saying? So that's kind of how you do it. So oftentimes I'm using GPU nodes, which luckily enough usually have fewer users, so I don't have so many issues running into other users. What's the supercomputer called? The one I'm using right now is known as Songo. I don't know what we can see. So Songo Oyst. Let me see if I can find it. In fact, it's actually Scion, S-A-I-O-N. I don't know if I'm actually... No, they don't have it publicly available. For the one that I'm using here, Songo Oyst, is here. So I guess I can just give you... There it is. There's an image. What do we have here? High performance computing. Oh, McCabe Lab. Okay. Yeah, fine. Songo. It stands for Coral in Japanese. Actually, this goes through and explains to you how to use it pretty well, honestly. They did a good job here. But yeah, it doesn't really matter what the supercomputer is called, right? Like, you guys won't have access to it. It's specific for our university. If you want a supercomputer that you can have access to, I think a good one is the Amazon EC2, I believe is what it is. Elastic Compute Cloud. Yeah, this is pretty good. You have to purchase a little bit of computing time, but overall it's pretty good and available for most people. So I would recommend this if you're interested. If you're doing GPU computing, quite frankly, the supercomputer doesn't help too much. Really, as long as you've got a good enough GPU in your system, that's all you need. However, as a note, the latest like V100s, P100s, all of these latest architecture, like latest and greatest GPUs, cannot be put into your desktop computer. And the reason they cannot is because they are passively cooled and not actively cooled. This means that they are cooled usually by a server, not cooled by like individual fans on the GPU themselves, right? So you have to keep that in mind, that if you're going to be running like really high performance GPU simulations, you probably cannot run them on your local desktop machine. But if you just need a GPU to do some simulation on, your desktop machine should be fair enough. Okay, so let me see if I can figure out what's going on with this N case. I don't actually understand why it's not working. So let's just look for capital N. Capital N here. So there it is. I just put it in there. It should be fine. It should be fine. There's case N. Break and wave function number. Interesting. So why is this not working? Rank quit. Make clean. Make. It's probably still not going to recognize it. So I'm gonna try to figure out what's going on with this parser. Why it's not recognizing the -N flag. And again, I'm sorry. This is just a bunch of grunt work. So like, if you guys want to talk about something else, just feel free to do so. I don't mind. I might not engage with the conversation too much, but you know, it's cool to talk about whatever you guys want to talk about. No problems. So we'll give this guy a second to build. I switched from Windows to Linux a few months ago. Oh, cool. Which distribution are you running on? I use Arch Linux, by the way. Okay, so let's go ahead and run this one more time. Let's see. Is the option? No, it says no option N. Unknown option N. Why is it unknown? Option requires an argument. Oh, I'm an idiot. That's why. Ha! Got it. Segmentation fault. That's exactly what I was looking for. Okay, good. So now we know something is broken, and we know that something is broken because we are, okay, great. So now we can kind of work from here. This is what I was hoping for. I'm going to try to run a very basic example here. So I'm just going to run GPUE. What if I run GPUE? I think it should be 256. Okay, it's just 256. So let's run this with an N2. Should segmentation fault? Great. So now what I'm going to do is I'm going to run CUDA GDB. Aha! I'm not able to run that here because I'm using this GPU for visualization. So I'm going to have to run this somewhere else. But I don't think I'm allowed to do this. So let's run GPUE. And let me just see what happens if I run R-N2. It's going to say, yeah, all CUDA devices are used for display and cannot be used while debugging. So that is a problem. I'm still using my Windows because of Microsoft Word. Yeah, admittedly, a lot of the people here at OIST, specifically people who need like Japanese input and stuff like that, they pretty much do everything in Microsoft Word. The reason a lot of people use Mac is because it's basically a Linux machine with the ability to use Microsoft Word. And so because of that, I think a lot of people use it for that reason. Like that's the only reason. But again, most of the people I interact with, like most of the code I write, has to be written for Linux because just almost every supercomputer in the world runs Linux, right? So if you're not writing code for Linux and you're doing supercomputing, I don't know what you're doing. What about LibreOffice or Wine? I mean, this is what I use. I use LibreOffice for most things. Admittedly, there's some small-scale formatting issues with LibreOffice that I wish there wasn't. But honestly, I do prefer LibreOffice to Microsoft Word when I have the choice, you know? So I tend to use that a lot. I think what I might have to do, I'm going to see what I can step through right now, because I'm sure there's a whole bunch of reasons why this is going to fail. So I can probably find quite a few of those reasons right now. Have to go see it. Thanks for another enlightening educational stream. Yeah, see ya, Art9K. Thanks so much for coming in. We might... Again, I said I was going to go to 11, so I guess we can keep going, but I'm just afraid there might not be much more I can do without my debugger. I feel like I need a second GPU on this machine, then contribute to it. That's the thing. I wish I could contribute to it, but I simply don't have the time, nor am I capable of just jumping into a new project, you know? I mean, right now I'm so incredibly stretched for the time I have, you know? And the way I see it is every person has their thing, their thing that they care about. I care a lot about open source software, but I care more about open source research than I do about open source software. So if I'm going to spend my time doing anything on the side, it's going to be developing a community of people that can do research together, not developing software that people can use. And admittedly, the software might be more important to a lot of people, but it's just not the thing I have time to do right now. If I did have time, I'd love to do it. I mean, one of the reasons I would love to be a full-time Twitch streamer or full-time YouTube content creator or full-time whatever online content creator of any form is because it would allow me time to do these open source projects that I don't have time for right now. LibreOffice worked for me, but sometimes when I make my computer crashing slides, they don't translate well in PowerPoint. Oh, yeah. I mean, I don't know. A lot of people use PowerPoint too. It's a very common piece of software to use. Okay, so I'm gonna see what I can step through right now, see what I can get done. Quit anyway, yes. Let me go ahead and get some more water, and we'll see how far we can get. We might not be able to get too much further, but honestly, I count this as a success of a day anyway, because we did get some stuff done, and I'm kind of sort of remembering what I need to get done. It's been a few weeks since I worked on this. I've got a bit of a timeline. I've got only like a month to work on this, basically, a month and a half. So what are you debugging? So the whole point of this simulation is to do multi-component superfluid simulations of Bose-Einstein condensates using graphical processing units. In fact, you could argue that the whole point of this simulation is to do massively parallel multi-component superfluid simulations of Bose-Einstein condensates on graphical processing units, hence the title. So when I added in the second component, which means a second superfluid working together with the first superfluid, we got a segmentation fault. And admittedly, there's a lot of reasons why this could happen. So I'm going to go through and I'm going to see what the problem is. Most likely, it's a problem with the initialization. We're just not able to initialize the second component correctly. I wish I could backtrace that to figure out what the problem is, but I just can't because the GPU is being used for visualization. So let's see what we got here. I'm going to do a quick ls here. Let me just go into vi source, source and init. And I guess I'm just going to look for a wave function number here. Okay, wave function number there. Check memory. Yeah, so I know we have enough memory. I'm not too worried about that. Have you ran Valgrind? I don't think I can run Valgrind for a GPU. I can run Nsight, but I don't think I have Nsight installed. Do I have it? Oh, I do have it installed. Well, let's see what happens if I just run Nsight. I haven't done this in a while. I haven't done this on this computer at all. Yeah, okay. Bah. I forgot how to use this entirely. Yeah, I forgot how to use this entirely. So let's see, home James git, repository directory browse. I don't want to do home projects GPUE. Where are we? GPUE? Okay. Finish. I hope I didn't just delete everything in that directory. Oh man. Let's see what we have here. Run. Yeah, I'll figure this out later. I don't understand GUIs. Alice here. Okay, I'll work on it. I'll figure it out. Okay. So, we have this wave function number here, which should be fine. Let's keep working on this. And wave function number there. Yep. 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 Okay. So the code wouldn't run. The code will not run if we don't have... So let's see if I can walk through this. Let's see if we can figure out what the problem is. Journal, new page before. Again, guys, if you have questions, comments, concerns, anything like that, just feel free to let me know. This is why languages like Rust are good. Honestly, I don't think you can use CUDA and Rust. I mean, can you? CUDA, Rust? I mean, the main problem here is, like, we're limited, right? I mean, save CUDA DNN wrapper. Even so, like, I don't know. I mean, you might be able to. I'm more interested in switching to Julia than Rust, honestly. Rust just isn't used very frequently in high performance computing. So like the reason we're using GPUs to begin with, right, is because you get a massive speed up with GPUs. Here, let me see if I can find GPUE. I'm just gonna Google. I don't know, I can probably find this. GPUE stand for GPUE. Dang it, Superfluid Simulator. Let's see what we got. New simulation methods. Fine, I'll just go here. I know it's down here in the comment sections. Pethick, White, Wittick, here. Okay. So here's the reason why we're using GPUs. So this is a website that did a benchmark of basically GPU superfluid simulators, right? So I'm just going to scroll down a bit. Here's the kernel execution time, right? So this is in log scale, so it's actually kind of much worse than it looks. But basically, lower is better. Blue is GPUE. Gray is their built Charter Suzuki MPI build for GPUs. Green is for CPUs, and pink is for a GPE Lab, which is a MATLAB toolbox. So going from MATLAB to C, you get a performance increase of about an order of magnitude, it looks like. It's going to be 37 times, something like that. It's like, here, what do we have here? GPE Lab is 1857. So going from this to CPU, it goes from 1857 to 50, right? So we're talking about not only an order of magnitude, like 220 times faster. What is this? 50 times 2 will be 200. Yes, that's 20 times faster, right? And then moving to the GPU, you get an additional 5 times performance. So we're literally 200 times faster than MATLAB code and 5 times faster than well-optimized C code. And so that's why you switch to the GPU, because you get code that's 5 times faster than, super well-optimized C code. And admittedly, we're still much, much, much better than, MATLAB code, right? Because MATLAB code is literally 200 times slower, right? So it's phenomenally slow. But getting this 5 times speed improvement on C is very, very good, because that means that you're approaching territories that people have not been able to really hit before for GPU computing. And again, this code takes literally a week to run sometimes for 3D simulations, right? So if we're 5 times slower, right, that means it's not going to take a week. It's going to take 5 weeks to run the simulation. And if it takes 5 weeks to run a simulation, I mean, come on, you're sitting there for a month just doing nothing. What, twiddling your thumbs? I don't know, It's just difficult to do, and people are used to this. They're used to this type of long, large-scale simulation. And so that's why we're moving to GPUs to kind of save the issue. And again, that was kind of a rant. I apologize for the rant, but what I mean to say is we're limited in the language choices based on what can use GPUs, right? So we have Julia, and we have C++, and really at the time of writing, when this code was written 5 years ago, or started to be developed 5 years ago, we only really had C and C++. There weren't really other languages that we could write in. So now, we're kind of stuck with what we have, and that's currently C, C++, Julia, and a few other languages here and there. Like there's a few bindings for Python, and there's also more bindings for other languages and stuff. But for the most part, I'm okay with what we have. There's issues, but I'm okay with it. This HDF coming soon has been there for years. HDF is never coming. Oh well, let me get some water here. Oh man, I have a bit of a headache too. Okay, so again, I think what I'll do is I will, I'll keep going for a few more minutes, see what we can do here. I've got a feeling that because I can't backtrace through anything and because I can't debug this right now, I need to run CUDA GDB. I need to run that. Otherwise, I'm not going to know where we are. Off topic, but I did the math, and each transistor in a 14 nanometer CPU is 7,000 times thinner than the average human hair. Oh yeah, I believe it, right? I've got some people I've got some friends working at Intel, and they're telling me like they have to deal with electron tunneling all the time. Like they have to deal with like really small scale quantum effects because they just have to deal with small scale quantum effects, That's just what they do. Because their processors are so small, and it's just how they have to deal with things. It's incredible how far we've gone as engineers. There was a comment earlier, I think by Tokdo. Is it Toko? I can't pronounce the name so well, but he basically mentioned that this is why you don't teach engineers quantum physics, and I'm like, well, I mean, they need quantum physics. Like nowadays, we're at the stage where you need to understand this type of stuff. Okay, so let me see if I can find this error. What I might do, there should be like a generate fields command here. And let's see, where is this guy in the large scale things? Let's set number. This is on 212. Okay, so let's see, it's on 212. Let's see what we set above this generate fields command. I've got a feeling I'm gonna do some really crappy, just like print out debugging. I know I'm not supposed to, but like I don't have a debugger available right now, and so I don't really know a better way to do this. So let's go into that generate fields guy. So we're gonna write and quit here, and let's go into VI source, and it should be operators, and I believe it should be generate P space, but I'm looking for generate K fields, gauge field. Here we are. Okay, so let's see what we have here. I'm sure it's probably in here somewhere. We have the wave function number being read in, so let's just look for where this wave function number is used. Wave function number is there. Then we have the wave function number being generated for a vector double. Okay, we're allocating that on the GPU. Aha, see, that's the issue right there. I'm a complete moron. When I did this initially, I think I just did this so it would compile, which means that all of the, oh, there's so much work I need to do then. Wow, should I get started on that now or should I do it tomorrow? So here's the issue. I knew when rewriting this code for multi-component simulations, I would have to rewrite every single variable, so it was basically a vector of vectors, right? So in the process of rewriting everything in vectors of vectors, I kind of cheated a bit, just to make sure we could get something to compile quickly. And so by doing this, I made it so that we basically everything is now a vector of vectors, but I only really initialize and work with the first component. And I know that's really dumb, and I'm really sorry that I did that, but it is something I'm gonna fix now-ish. So we'll kind of go through and see what we need to do. Don't they make a template, put some fluid on that react to light on a wafer, and then use some UV light to imprint the design? I honestly don't know. You're gonna have to talk to, I mean, maybe Oh Bother would know. I mean, he does a lot of this type of stuff. I'm honestly not sure. Yeah, I'd have to ask them. I know that, like, you know how like you have i7, i5s, i3s, and all that kind of stuff? Basically, like, they don't change the process to design an i3, an i5, or an i7. Like, the process to make all of them are the same. It's just the processor turns out to be an i3 if it was just, you know, there was a lot of error in the process, and it turns out to be an i5 if there wasn't as much error, and an i7 if there was even less error, you know what I mean? So it's basically like they're doing the same fabrication process. It just depends on how crappy the processor turns out. That determines how they brand it and sell it, which was a very interesting thing that I heard them talking about. So what I'm going to do here is we have the wave function here. It's allocated correctly, so I guess what I'm going to do is CUDA malloc. Okay, let's just try this out then. We're going to say, let's see, for I equals 0, I less than, we shouldn't use I, we should use W because that's what I'm using in previous notations. W for wave function number. Then we're going to do plus plus W, and that should be okay. And then I guess I'm just going to have to go through all of this, generating wave function. Yeah, all of these guys are all just going to have a W instead of a 0. And in principle, I think that should be okay. Parse store. So up to here, I believe. Okay. So let's just go ahead and add in 4 spaces there, and let's just see what happens. Oh my word. Oh, this is what I get for being crap at programming. I know I could do this in a different way. I'm checking each line as I'm going through to see what I need to do. Sorry about that. Yeah, okay, so there's a lot of these guys I need to update. Let me just move up a bit. Oh, ooh, this stuff is something to do. That's okay. It's okay. We'll get there. Could have been copy V0. Where's our big for loop that we had there? It should be here. Okay, so we're gonna do this line. Yeah, there's a lot to do here. It's okay, we'll get there. Whatever, I'll just... Yeah, that's what I figured. Bah. Oh, I think I went too far. That's okay. I'll just do 4x here. Okay. This should still compile without any problems. Crap. Of course it doesn't. We're gonna switch I to W on the second term in the for loop. Yep, probably. Yep, thanks. Hello. Why did it not compile even? Identifier, blah, blah, blah. W is unidentified. That's because I need an int. Okay, I is unidentified. Nah. Why? I didn't even do anything but add in a loop and indent it. Okay, well, let's just pop through here. Wave function array is unidentified. 967. I don't understand. Oh, I do understand. I do understand. Yep, out of scope. Okay. Well, we're gonna have a lot of work to do. That's okay. Yeah, let's compile it. Nice. Too much work to do. Let me go ahead and get some water. Yeah, so there's a lot of this grunt work to do. It's gonna take a few days of me just working on this and just getting it all to work out and all that kind of stuff. Let me get a little bit of water again. Okay, it does compile. And I guess what I'm gonna do is I'm just gonna go through line by line inside this for loop, and see what we can take in, or take out, and see what we can do. Okay, pop down here. Generate fields, that shouldn't be, should be here. That's what I'm looking for. Okay, so for W, and again, so this line, I think all we're gonna have to do is change this 0 to a W. Shouldn't be too big of a deal. And CUDA malloc, we're just gonna malloc this guy. Fine. Okay. I don't think there's much we have to do here. If par is AST GPU V, this basically means, again, as I mentioned a few hours ago, and again, this is a bit weird. Sometimes we store our variables as sometimes we store our variables as abstract syntax trees instead of arrays. And so what I'm doing here is asking if it's an AST on the GPU. Use Vim without syntax highlighting. Yeah, I mean, I use VI, actually, not even Vim. That's why we have a Simul VI. Yep, that's what I use. I'm sorry, it's just, like I said before, because I do everything on an SSH, I'm SSH'd onto something, this is just what I use and what I like. I don't judge other people for using different text editors. I mean, it is what it is. They use whatever they want. I don't mind. It's okay. But I mean, this is just what I use and what I like. I don't really like syntax highlighting. It just kind of bugs me out. It makes it harder for me to code because there's just a little bit more thought I need to put into coding when I code with a syntax highlighter. You know, like it just makes me like all of a sudden now, like when I type in stuff, it just turns in. It just like changes color and stuff on me. It's just so weird. If your mother comes up to your room, tells you how to clean that room. Yeah, it's basically, it's true though. Yeah, this is kind of how it is. And again, most of the time I'm SSH'd into a system, right? And because of that, it's kind of a bit weird to use like non-terminal text editors. Yeah, so I'm here doing the research stream. So usually I do my stream from 5 to 7 o'clock a.m. Japanese Standard Time, but I'm also doing an additional research stream. So this is actually my work time. I'm just doing work on stream because I'm trying to find ways in which we can do research in a kind of more open way. And I thought streaming it would be as open as you could get, right? So I'm kind of, trying to find ways in which we could stream research and it'd be actually genuinely enjoyable for people and fun and all that kind of stuff. We'll see how it goes. I'm kind of, oh, hello there. I'm not really sure how these streams are going. So like, if you guys have questions, comments, concerns, or, you guys think anything about it, just let me know if you guys have thoughts, opinions. Because again, what I'm showing you guys right now is legitimate research. Like it's legitimate work to do research that will eventually be published. So it's, that's the issue there. I should generate these wave functions above. Is there a programming language made for processor design? There is probably. Is me or does the voice sound different today? It's probably because I'm a bit tired. Honestly, my voice is a bit raspy. Just because I've been speaking for so long. I've been speaking for like 5 hours almost. So it is a bit longer, and I'm also a bit more tired than normal. Just because I'm more tired than normal, So I guess I should generate the wave function up there. So let's go ahead and do yank, actually D4D, and we're just gonna pop this up here for where we generate the SC vector double this guy up here. Okay, so we don't reallocate those guys. Pop down here, and we're just gonna set those guys there. So we're gonna do RW, U. Yeah, let's take a look. Language for instruction set architecture. Oh, I'm gonna have to highlight that, aren't I? Let's give that guy a go. Paste it here. Sorry, I was checking for notifications. Unfortunately, my side screen is covered by the arm that holds up my microphone, so it is sometimes obscured a bit. Okay. Let's keep going. Also, I haven't been looking at notifications too much. Yeah, I apparently haven't really been getting any notifications, which is fair enough. That's not what I'm looking for. Why did that not do what I expected it to do? 1 second. Copy. Interesting. Why did it do that? Okay, I don't understand what happened there. Okay, that's fine. Lisa, language for instruction set architecture. Is language to describe the instruction set architecture of a processor? Oh, interesting. Cool. Hey, Fox. Hello, Simplevar. How are you? I hope you're having a wonderful day. Okay, CUDA malloc. I believe this is fine, just mallocing in the middle here, because again, we're allocating a specific wave function there and there. This should all still be fine. Okay. Winding. Yeah, this is fine. I'm not seeing any problems here. Okay. I'm just going to walk through this one step at a time, making sure I'm trying not to miss anything. So if I'm not super active in chat, that's fine. I apologize for that. Let's see, wave function number. Aha. So all these auxiliary fields then should also be generated up top. So what do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11, so we're going to do D12D. And then we're just going to paste that up here. Here it is. So we're just going to paste it there. And I'm just going to remove some spaces. So for X, there. Yeah, it's fine. Okay, cool. So let's pop down here and let's keep going. Again, if you guys have questions, comments, concerns, ideas, anything like that, feel free to let me know. Last time I watched you was like a year ago. Yeah, I vaguely remember. Yeah, I mean, I remember you being around. Yeah, how have you been? Let's write that. There we are. And there. And we keep going. You started talking, huh? Wait, what? What do you mean I've started talking? Ever since I've been streaming, you might be thinking of a different streamer. Like I'm a super active streamer. Like I always talk when I'm streaming. Let's see. Have you tried doing any CTFs? CTF stands for what exactly? Something fluid? Maybe I remember on a tired day. Maybe you don't remember me so well. Capture the flag? No, I haven't done any of that. Because honestly, I've never not talked on stream. I've always been incredibly talkative. Oftentimes too talkative and too rambly. So you might be thinking of someone else. Nice. Sorry, I'm kind of popping back and forth. Josh, thank you so much for the follow. Really appreciate it. Keep going. And there. Or too busy with matrix math? I mean, I don't know. I just feel like there's never been a stream where I have not been very active with the chat. Let's see. Oh, this is such a pain. I have to change all these. I know I could just search and replace. I needed to do that, but I'm kind of invested in this right now. So I'm just gonna kind of go through and. No, I've never done a fluid simulation on this channel before. I did a light simulation before, but that was a super long time ago. But you were talking with less energy? Maybe. There was one time when I was doing a light simulation not too long ago where Gustorn kept coming in and he was constantly like, oh, you should do this, you should do this. And I was just like, man, come on, like, let me do my thing. I had this discussion earlier, actually. It's a pain in the butt. I had this discussion earlier today where I kind of don't like it, like doing puzzles and stuff on stream, because to me, like, part of the fun of doing programming to begin with is figuring out those puzzles and stuff like that. So having people kind of like spoil the plot for you and kind of walk you through the puzzles, just, it kind of ruins the sport of it, you know? And so sometimes I might have gotten down, so you might have watched one stream in particular, because there's only been one stream where I was genuinely sad during the stream, because everyone was talking and it was just super annoying. So if you watched that stream, then maybe, but that was like 2.5 years ago. So I highly doubt that was the stream you watched. Let's keep going. I remember that one stream. I just wasn't having it that day. So I'd be very surprised, but maybe that was the one you watched. Yeah, okay. So maybe it was something like that. Let's go ahead and right there. Oh, shoot. Oh, no. Let's go ahead and XXX. No, I used to be, in my opinion, and again, this is just my opinion, I used to be way more excited, specifically more excited than I am now. I'm quite exhausted right now. Could have free, yeah, okay, so we're just freeing all these guys up. Yep. Okay. And now what I'm going to try to do is put the end of the loop here. And just see what happens. I'm going to try building this. Let's go here and let's just run make. Hopefully it builds. It looks like it is. Nice. Okay. So let's go ahead and remove some spaces here. And I'm going to run a simple simulation just to make sure it works. Not with multi-components, just with a single component. And we're going to see how it goes. Yeah, sorry, I'm not trying to say you're wrong, Simple Var, by the way. I think you're right. It's just, I used to be way more active, like way more excited about the programming and stuff like that. But now it's just been so long. I think the simulation you're talking about, and again, this happened so long ago. Let me go ahead and CD into Project Simuleos. Actually, maybe 4 years ago, honestly, would be, let's see, CD into, not geometrical optics, probably FDTD. LS here, CD evanescent, LS, let's see, what do we have here? I should have a, simple data.that. What happens if I just run GNU plot evanescent.gp? Something like this, maybe? So this was a finite difference time domain simulation where we were simulating basically light moving through this weird optical fiber type of cavity, something like that. And this is what you're talking about, then yeah, this might be it. Oh man, we spent so long on the simulation. A video didn't even come out of it. Like we just we did it and then stopped. If processing information makes something conscious, what stops processor from being conscious? Let's see. To be fair though, usually when I was doing those simulations, and even these simulations now, right? Like I do all of the streaming I do is from 5 to 7 o'clock a.m. Japanese Standard Time, right? And so like, I kind of give myself a pass if I'm a little bit tired or a little bit, groggy or something like that, because again, it's 5 in the morning, right? Like, being up and talkative at all at 5 in the morning is kind of a lot. If processing information makes something conscious, what stops processors from being conscious? I don't know if I'm qualified to answer that question. Projects GPUE, LS here. Let me do a quick, I'm just gonna run the previous simulation that I ran just a second ago, and just see what happens. This should break, nice. So let's try running it here without that, and I just wanna get the same results that we got before. And then I'm fairly confident in saying that a lot of the problems that we're having right now has to do with the fact that I was just a crap coder, and when I initially created, or I initially put in the multi-component simulation, I basically just put in stuff that would work, not stuff that actually made sense. So that's kind of the next step. So I'm gonna have to basically do what I just did for all of the initialization steps and everything else. And there's a lot of stuff to do here, but that's okay. We'll get there one step at a time. I'm not too worried about it. I might do some of it at work. Could you provide a counterexample? I just don't know. I can't provide a counterexample. I'm not sure if I can really talk about this. Yeah, just because I don't really know. I mean, the definition of consciousness is so vague. There was a book I read some time ago about consciousness. It was, do I still have it? Give me just a second, guys. I might have it. One second. Never mind. I'm not going to pull that out. There was so many books on top of books on top of books. And there was just stuff. It was a mess. There was no way I could have pulled that out easily. So we're going to cd into pi, and we're just going to run the last Python. Yep, looks like the simulation is identical to what it was before, which means we didn't screw anything up too badly. I'm going to run GPUE-U just to run the unit tests. And just to make sure that's working too. So GPUE-U. But I think we're okay for just a single component thing. And so now we just have to do that for all the other initializations, and we just have to work through everything and just see where it's breaking and fix all of those errors. So I've been streaming for about 2 hours and 30 minutes on the on this particular code base. I'm gonna probably close shop pretty soon while these unit tests are running, or after these unit tests are done. I'm probably just gonna commit what we have. And then I'm going to work on it, not necessarily later today, but I might come back tomorrow and work on it then. I've got to work on a paper this afternoon. I really need to get a figure done on a paper, and if it's just not done this week, I don't know what to do. I've been working on it. It's one of those times when the simulation has just been running for a week and it's still not done, and it's just so much left to be done for that paper. But it's like right there. It's just, I still see so many small details that need to be fixed. And this will be the last paper, really last physics paper of my PhD. And I'm pretty excited for it because it means that from now on, after that paper is done, I can work exclusively on like compressed sensing and stuff that I'm kind of more, I don't know how to put it. I'm more excited by, more computer science, less physics. And don't get me wrong, I like physics. It's just, it's not, it's a bit different. Let me go ahead and go to, here, let me just run the last. Here, so this would mean that I am at, just for the record, just to keep you guys up in the loop, so that'll be my 4th paper that I'll be submitting. So I just finished my first 3 papers. Admittedly, I'm second author on this one, but I have 2 first author papers, so that would be my 3rd first author paper. And then there's a 4th first author paper that should be coming out from the internship over the summer. And obviously I'm writing my thesis right now on compressed split-step Fourier methods for simulating quantum systems. So there's a lot of stuff to do. But we're getting there, and I'm pretty excited by it. Let's go ahead and see who's online on Twitch, and we'll just kind of wrap it up, talk about some things. Mr. Orlist, yeah, we can host him. He's quite nice. I'm a big fan of his stuff. Yeah. So what do you guys think about these types of streams, guys? Admittedly, I'm very interested. Wait, before you guys go, I'm sorry. I just want to have a brief, just meta discussion here. These types of streams are kind of like, they're very interesting to me, right? So this is like actual research being done, right? And so it's kind of, there aren't very many people who are doing like actual research on Twitch. There are some people who talk about research, and I certainly talk about research a lot. But I'm just wondering what you guys think about this in particular. It's a bit, how do I put this? It's a bit slower than our traditional stream, right? Because it's not like we're going through algorithm or anything like that. It's just kind of like, hey, we're just doing grunt coding that is necessary for the future development of the GPUE code base and stuff like that. I should be more cognizant as I do it more, and I do want to do more streams like this because I feel like if we could get people engaged with research, like that's really part of my goal. And it's something that I'd really like to see. So I'm just interested to see what you guys have to say. And also, change of pace is usually good for everyone here and there. Yeah, that's fair. So what I was planning to do, oh man, I have a headache. What I was planning to do was do kind of a GPUE stream every day. So I do my normal stream from 5 to 7 o'clock a.m. And then I do my GPUE stream, which is going to be a specifically research stream from basically 9 to noon, somewhere in this range. And the plan was, it's still 5 hours of streaming a day. There's a lot of streaming. But the plan was just kind of get people as involved with the research as possible with the hope of maybe even getting people to help out with the research here and there. Josh, I live in Okinawa, Japan, particularly the Okinawa Institute of Science and Technology. So OIST, you can just Google OIST images. So I work here. It's just a picture of OIST. It is it's an interdisciplinary research institute that, I don't know, it's a super nice place. I would definitely recommend going there. I speak a little bit of Japanese, not enough to really be fluent in it, but enough to be able to carry my own in Tokyo and stuff like that. For the most part, OIST is international. It's pretty diverse. Like my lab has like 18 members in it, and there's only like 1 or 2 countries that are represented more than once, So like we've got like 15 countries represented in a unit of like 20 people. It's quite a lot. What window manager is that? I'm currently using OpenBox. In particular, I have my own theme for OpenBox that I use. How many people do you think there are as smart as you? You won't find that much help in Twitch. To be fair, I found a lot more help on Twitch than I have on YouTube so far. Because there is a genuinely good programmer community here on Twitch, but not really on YouTube, And so even though I've got, 50,000 plus subscribers on YouTube, who cares, right? Like they're not providing me any useful information. They're not helping me out with research. Meanwhile, people here have been. Do most people live near you live? Wait, near you? And most people that live near me speak English because most people that live near me live at OIST. But outside of that, it's kind of spotty. I think a lot of people know about English and they can kind of understand a bit, but they don't know it well enough to converse with you, right? So for the most part, they speak Japanese, and in some ways a bit of weird Japanese too, because they're Okinawans, so the dialect is a bit different. But research stream slot sounds cool. Yeah, that's what I'm looking for. Not that we're stupid, you're just way ahead. I don't think that's true. As I said before, I don't think I'm any more intelligent than anyone else. I really do genuinely believe that anyone can engage with research. It's just they kind of put themselves down and think they're not smart enough, or don't put in the effort to learn and understand it. And I just kind of want to be the guy that helps people learn and understand it. That's kind of where I want to be. Ideally, I'm kind of debating between doing a bunch of different things. Obviously, I'm not particularly popular on Twitch, but I am quite popular on YouTube, and I could be an independent researcher, flipping between YouTube, Twitch, the algorithm archive, all this kind of stuff, if I wanted to be after I finish my PhD. But in actuality, I'm probably looking more towards creating a research lab or something like that, that incorporates live streaming into the research. Like we always have some sort of live stream or some sort of open research discussions or something like that for people to join in on and discuss with. Because I do genuinely believe that researchers need to do a better job at engaging the public with research, and this is one of my attempts at doing that. So I'm going to start making videos on all my research. I'm going to start doing a whole bunch of other stuff on research. So anyway, I think that's it for the day. I'm happy to hear that you guys don't hate these streams. Admittedly, viewership is a bit low, but that's okay. An educated research? What do you mean an educated research? Mate, I think a group of people need to buy a couple thousand Raspberry Pis, network them together, and make a supercomputer. I think that's been done, but I think the Raspberry Pis simply aren't strong enough to support the massive computation that needs to be done. Teach people the skills of researching. Yeah, that's true too. I think that's another important aspect of this. Okay, so I think that's where we'll stop for the day. I'm happy to hear that you guys are happy enough with continuing this. I'll be back again tomorrow at 5 o'clock a.m. for my typical 5 to 7 stream, where I do, I'm not really sure what, but we'll do something, and probably discrete Fourier transform stuff. And then we'll come back tomorrow from 9 to 12, and we'll do GPUE development and stuff like that. I'm hoping I'll be a little bit higher energy and stuff. I don't mind doing some more chill streams and stuff like that on the 5 to 7 stream. Point is, I just want to engage people with research and stuff like that. Okay, guys, have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. If you haven't already, please feel free to check out Discord, where we just chat about things. It's actually a pretty good Discord. There's a lot of discussion happening a lot of times. And yeah, that's about it. So see you guys, and I hope you guys have a wonderful time. Bye, guys.